Hello everyone, good day, and I hope you are doing very well. Welcome to the new chapter in thermodynamics. This chapter will include the energy and energy transfer and general energy analysis. As you can see in the chapters, in the lecture notes and the slides that I sent to you in the classroom, will be the slides. What we are going to talk about the energy is how the energy will go and how can we take benefit from the heat energy and heat transfer. As you can see in this slides that we have this is a renewable energy system that we have a sun. Will give you a sun. Heat from the sun will go to the cells. This is the solar radiation cells, and from this one the electricity will go and will heat the hot water from the tank and we have a pump. We need the electricity for the pump, and will be circulated. Already we need the cold water to hot the cold water, and then this hot water go to the house and so on. So designing a solar collection involves a thermodynamic, heat transfers, and fluid mechanics. I know we have in this chapter we are talking about how this heat transfers from the sun to the hot water. We have a definition for the enthalpy, and what is the enthalpy is how much the energy that we have for a stationary fluid. For example, if I'm talking about 1 meter cube of stationary liquid like water, so for example if this water was a hot water, so how much is the BTU, or how much is the joules or the heat that we have in this liquid and this fluid? It's called the energy that's included, the internal energy. This is the internal energy. Now beyond that one we have another energy which is called the PV, which is the flowing fluid. Also the flowing fluid, we have an energy due to this one. Usually it will be, if we have a dynamic, it will be V square over 2G and so on. So the combination of these two energies are called enthalpy. So enthalpy is the internal energy that we have plus the motion or the fluid that's flowing, the energy that's going to induce by the flowing of the fluid. That's called the energy. So flow energy, which is the PV, is representing the flow energy of the fluid. It's called the flow work. Now we have the ideal gas flow. You remember this equation, which is the P and the V, which is the pressure, and this is called specific heat, and the R and the T, which is the temperature, and this is the R, which is the let me say it's the gas constant. Now this equation is called the ideal gas relation. Means that for example increasing the pressure will affect directly on the temperature, and making the temperature will will affect on the pressure, and so on. Now you can see this will be the same equation, because V is the specific here's the specific weight, means how much meter cube per kilogram will be there. Now we have a rho, which is the density, is equal how much kilogram that we have in meter cube. So nu, or the specific volume, is equal to 1 over rho. So it's the same that we have here. So P is equal to rho RT. Now we have a term which is called specific heat. What is the specific heat is meaning? It means that if I have 1 kilogram mass of any substance that we have here, and its temperature, for example, it was 20. Now if I want to increase this 20 to become 21, so what should I do? We should add a kind of, for example, candle or anything, any heat, fire. So fire Now this fire will help this 1 kilogram of this substance to increase its temperature from 20 to 21. Now how much is this quantity of this heat or of this energy have been added to this 1 kilogram? Is 5 kilojoules. So 5 kilojoule was added to 1 kilogram of this substance to increase 1 degree of Celsius. That's called the specific heat. So specific heat is the amount of the heat that's needed to be added to one specific a certain mass to increase its temperature from for 1 degree Celsius for delta T. Now this is the meaning of the specific heat. Now we have two types of specific heat. We have the specific heat while we are making the volume to be constant. It means 1 meter cube of this substance, I want to just increase 1 meter cube of this substance 1 degree Celsius or 1 degree 1 Kelvin. So what how much is the kilojoule that is needed to increase the temperature of 1 meter cube from this substance to be to increase. So now without touching the volume, without any increase in the volume, that's called the specific energy that is needed just to increase the heating value or the temperature of that water, of that substance with having a constant volume. Now sometimes this is usually for the gases, and usually for the liquids like water, the specific heat at constant pressure, or let me say when we want to just increase the heat energy or the heat for a substance without having any pressure, without touching or making the pressure on that body, on that mass the same, not to increase any pressure on that one. That's called the specific heat while we have pressure make constant. So now the C, which is the constant, the specific heat, we have two types. Either it will be C sub V or either it will be C sub P. This is with volume constant. So how much kilojoule will be per kilogram per degree or Kelvin or Celsius without having any change in the volume, and Cp also how much kilojoule per kilogram per degree Celsius or Kelvin with having the same pressure without change in any pressure. That's the thing that we have. In the low pressures, what means that if we have normal or natural heating, there will be low pressure. At that low pressure, or the real gases, I mean by the gases, approach ideal gas behavior, and the ideal gas behavior means that the specific heat for the pressure will be the specific heat for the with having a volume constant plus the R, which is the constant of the gases. Now here's one of the interesting examples. Here's one we have a mass of 1 kilogram of air. Then we have the degree of this one mass, 1 kilogram air is 300 Kelvin. By the way, 300 Kelvin, the Kelvin, it means that equal to degrees Celsius plus 273.15. Now means when we have the Kelvin equal to 0, it means C equal to minus 237.15, which is the absolute zero. When we have about 24, so 23 means by that one, so the Kelvin is equal to 300. So this Kelvin means at room temperature. Room temperature means temperature is equal to 24 degrees Celsius about. So if you have 1 kilogram of the mass of the air and you want to increase this 24 to become 25, for example, if you have a split in a room and you have to increase the temperature from 24 to 20 plus 1 degree Kelvin. So what will be happen? There will be, you need at least 0.7818 kilojoule. Now there is another thing that we have. If the room temperature was already it was hot and you want to increase it into also hot, but it's more, so 1000 instead of 300, it was 1000 Kelvin. So what you need to increase, you need more energy. So it's already hot water, so you need to make it hotter. So by 1 degree Kelvin, 273. So what do you need? You need more energy. So it means that the specific, if I have a temperature and we have a specific heat, for example C sub V, so what will be happen, or C sub P? So increasing the temperature will let you you need more specific, more kilojoules it needs while we have low pressure. That's what we have, the relation between the temperature. So the specific heat, which is Cp or Cv, the same, are of any substance change with the temperature. Now increasing the temperature means you need more heat. Here's some definitions that we have. The 1 kilojoule per kilogram per degree Celsius is the same that 1 joule per gram per degree Celsius. 1 kilojoule per kilogram per Kelvin, it's the same. And we have the du, the amount of the internal energy that we have, it will be depend on the dt. It means that, as I said, that if you have temperature and the u, which is the energy, so increasing the temperature will help you to increase the internal energy in temperature with the u. And also heat, which is the dH, here's the enthalpy. These are two values of enthalpy, and this is the flow work. Also having the flow work will depend on the pressure, and it will be increasing the temperature will help you to increase the H. Now it means that usually this will be measured in Kelvin, will be measured in kilojoule per kilogram per Kelvin. So what will be happening, we will have the delta U, it means how many kilojoule will be per kilogram, and if I multiply this one by the mass, I will get delta U in absolute, how much kilojoule will be there. The same that we have here. Also the dH here will be kilojoule per kilogram per Kelvin. This is Kelvin, and the Kelvin there will be kilojoule per kilogram, and if I multiply this is by mass, I will get the value of the delta H, and if I add them all together, I will get how much kilojoule will be the net net energy will be there. Now this is for sometimes we have for any materials that can be compressed, like water, like fluid, like gases, and so on. But sometimes if you have solid substances like iron, so what will be happen for these kind of materials, the specific volume, which is how much meter cube per kilogram will be there, or density or rho, does not change with the temperature. So be careful that the me, which is how much meter cube, the specific volume, and the rho, which is the density, how much kilogram will be per meter cube. These two factors will be affected by temperature and pressure, as we have the P nu MRT RT. This is the real gas or real fluids equation. Now for the solid materials, for the solid like iron, for like rock and so on, these two factors will not be affected by the change in the temperature. That's called incompressible substances. So in this case, the constant volume and the constant pressure, heat value, specific heat C sub P and C sub V, these two values are identical for the incompressible. They are identical, means that they will become equal to each other. Now Cp will, for example, for 1 kilogram of iron, if it's in room temperature, so the C, which is the specific heat, this will be C sub V and will be C sub P, and it's 0.45 kilojoule. So means you need 0.45 kilojoule for changing the temperature of this iron from 25 to make it 26 degrees Celsius. The degree, the 25 to 25 to 26. Now this is per Kelvin. Be aware, this means from 300 to 300 something. Now we need 0.45 kilojoule per kilogram per Kelvin. Now this is the identical. It means that this is because of this iron is incompressible, and identical, it means specific value Cp and Cv, they are the same. Now it's time to talk about energy transfer. We say that the energy we have, it's in two manners. Energy can be transferred either as a heat or as a work. So heat or heating and will help you to know that there will be a change in the energy, and there will be also work. Now so the energy rate, it means that how much rate, it means that there is a per area, the amount of heat that transferred per unit time, how much kilojoule have been transferred per unit time. Heat flux is the rate. It's a rate of heat transfer per unit area, normal to the direction. Normal means perpendicular to the direction of heat transfer. So if I have, for example, in this wall, and point here and a point this way, there is a point here. Let me point 1 and point 2. So if I want to see, for example, the temperature here is higher than the temperature is here, so what will be happen? The energy or the heat will transfer from point 1 to point 2. So the direction, let me say the direction, if it was normal to this area, so how much is the rate, how much is the heat, how much kilojoule was transferred per meter square for this area? That's called the heat flux. Now, so the heat transfer rate and the heat flux, this is per unit of time, for example, per hour or per something like that. Now, kilojoule per unit of time, look at this one. If I have joule per second, that's watt. So kilojoule per second will be kilowatt. So kilowatt is the rate. It means that when I say that the amount or transfer rate, it means how much amount of heat, which is the kilojoule, measured by kilojoule. Per unit time, it means per second. Now this is will go and give us watt, how much watt have been transferred from point 1 to point 2. This is called the heat transfer rate. But the heat flux is the kilojoule per meter square of this area. So how much it will be? It's the heat rate, the rate of heat. It means how much kilowatt have been transferred from point 1 to point 2. So basically we have the Q, which is the watt. This is the kilojoule per second that have been transferred. This is called heat transfer, and by the way, this is dot, it means the rate. This is the heat transfer rate, kilojoule per second, which is the watt, but small q is the heat flux. This is the heat flux, which is measured by kilowatt per meter square. This is the heat transfer rate. So the heat transfer rate is how much energy, how much kilojoule have been transferred per unit time. That is, in this area that we have 3 meter by 2 meter, which is the area is 6 meters squared. Now if the transfer rate was 24 joule watt, it means 24 joule per second will be transferred from point to another point. That's called the energy transfer rate. While the heat transfer rate, while the heat flux, it means that, okay, per 1 meter square of this 6 meter square, how much it will be? Each 1 meter square of this 6 meter square, how much it could be holding? That's the 24 hour watt divided by 6, which is 4. So each meter square of this area will can help to you to transfer 4 watt. That's called the energy flux or heat flux, sorry. And after we know that there is a heat transfer rate 24 hours. Now it's time to know, okay, for how many times, for how much, for example, if I want to see for 2 hours, how much it will be the power. The power is the work done per unit time. Now this watt will be done by how much watt hour will be done. So just simply I will multiply this Q by delta T to get the watt meter that we have. That's the kilojoule again. And if I have we can say, yeah, this is the definition of heat flux. Now we have another definitions for the energy balance for the steady flow systems that we have. For example, if the flow that we have in a pipe, mass flow rate flow through a cross sectional is equal to the product of the density. Now we have the flow in this pipe is having a velocity like V, so this V times the A with the cross sectional area, that will give you Q. That means how much meter cube per, for example, second that will flow in this pipe. Now when I multiply this by the rho, which is how much kilogram per meter cube, will give us a mass rate. This is the mass rate. So mass rate is the how much unit of the mass that will pass through a specific point. This is the mass rate. So mass rate is equal to rho, which is the density, times the V, that's the AC. This is the mass rate, and the V, which is the velocity that we have, is equal to V times the area. And this okay, you can say the mass rate divided by rho will give you the meter cube per second, and this is the rate, transfer energy rate. It means that the mass rate multiplied by H. So delta H here should be careful. This delta H is equal to C sub P, and this is the flowing work. The specific energy when we have a pressure constant and the delta T that we have, how much is the delta kilowatt that we will have through this specific. And this is in steady state. So this is the definition of mass flow rate. This is the mass flow rate, I'm sorry, and the volume flow rate. Definitely, if I have a point in this pipe, for example, this is point 1 and there is a point 2 here. So if I want to see how much is the energy have been transferred from point 1 to point 2, and if the point in this point the temperature was T1, temperature here was T2, so T2 minus T2, and this is the delta T that we have, times the C sub P, which is the specific heat when we have a pressure constant, times the mass rate. That will give you how much is the kilojoule have been transferred from point 1 to point 2. So if the T2 was less than T1, so it means the energy has been transferred lowering, and if we have positive, it means that we have increase in the temperature. So the direction of the flow, this one, if there is an increase in if the E it was positive, it means that the temperature here is greater than temperature that one. If the E was in negative, it means the temperature in this point will be less than this one. This will be under the static condition and the net rate of energy transfer. Now it's time to talk about the heat transfer itself. So how the heat will be transferred? The heat will be transferred in three ways. It will be transferred either in one conduction, or convection, and radiation. So we have three ways to transfer the heat, or how much kilojoule will be transferred from point to another point. Now the conduction, it means that this is the definition of the heat transfer, conduction heat transfer. It means that if you have, for example, a wall, a surface, a body like this, and the temperature in this one, for example, if it was 20 degrees Celsius, anywhere, any point on this surface, if the temperature was like this, so if I take any point on this surface and I measure the temperature on this measure, it was 20. Now, for example, here was 50. If there is at any point above the parallel surface on this, but it was 15. Now we have a hot surface, we have colder surface opposite this one. So what will go? The heat will go transferred from this point to that point by a meaning of conduction. This is called conduction. Conduction means this will be the direction of the heat transfer. The heat transfer will be from the higher temperature value to the lower temperature value direction. So, and also it's very important to know how much is the thickness of this surface of this body. So as much as we have higher value of the thickness, so the heat transfer will be very low. And if I have a very thin plate, the transfer will be very high. So that means if you wanna, for example, boil 1 liter of water, and you split that 1 liter of water in a pot that having a very thick bottom plate, so you need the transfer of heat from the candle to the compliance to the water to the 1 liter will very need time. But if you have a thin plate, for example, very thin plate pot, that means that you need less time and they will be quickly boiled. So that means the thickness will affect directly on the rate of the energy of the heat transfer. Also, if you want to do it for an area, higher value or higher area, and a small area, it will also depend. So the heat conduction will depend on this area, and also with the delta X, this is proportionally will increase the conduction, and inversely with the delta X. Now the last thing that is remains are the delta T. So how much is the delta T? It means that we have 20 here and we have 50. So the energy will be 5 degrees Celsius change. Now it will be depend if there is a 60 degree here and here is 15. So the rate of energy will be quicker. That's the high. So the delta T, if I have delta T more, it means the conduction heat transfer will be higher than this one. Now this is the equation of the conduction heat transfer, it will be depend on the A area, delta T and delta A. So we have a constant here, it's called conductivity. So the conductivity, it means how much it will be, it's the property of the material itself. For example, is that material will help you to conduct the water, the heat faster or slower. For example, if you have a copper, it will help you to conduct very quickly. That means that it has a very high value in K. A low value of conductivity, it means that this material will not help you to for heat transfer by conduction. Now this is the thing that we have. For example, here's for two materials like copper and like silicon. So, and if I take 1 meter thickness of 1 meter of this material and 1 meter of the copper, and also there is a 30 degrees Celsius here and 20 here, the same for here. So what will happen? The amount of the heat transfer from the copper will be as we have K equal to 401 watt meter Kelvin. So I have to multiply by the Q conductivity, it's equal to K, it's 400. This will be 401 Kelvin watt meter Kelvin times the area. If I take the surface area of this one as a 1 times delta T here is 10 degree and divided by delta X, which is 1 meter. So that will give you about 4010 kilowatt is the amount of the heat. This is heat transfer. And now if I use a material like silicon, the silicon's conductivity is less than the copper. It means that it will not help you to transfer. It means that this material's resistance to heat transfer. So that's why we have 148 per 1 meter per Kelvin. That's what we have here. So it will give you about 1480 watt will be transferred for the same condition. The negative signs means that we are going, if there is a negative sign, it means that the equation ensures that the heat transfer in the position of X, in the positive X direction, and it's a positive quality. Now look at this. This is the conductivity values of the materials that we have. Look at the diamond is the material that will, the first thing, the very high value conductivity. It means it will conduct, it's very helpful for conducting the energy, the heat transfer. And after that we have silver, and then copper and gold. Now look at the last thing that we have, it's the air. So the air, it will help you to just transfer 0.026 watt, while we have 2000. So it means we have about 10 to the power 4 to 10 to the power 5 difference between the silver, copper and the air. Means that the air will be very benefit if you just want to make to resist, or you don't want to change. For example, if you want to for the construction of the isolated wall, so you have to make air in between the two walls, two layers, to just not let the heat transfer from a point to another point, while for the air and for the gases that we have. Okay, for the brick, look at the brick. For the brick, it's 0.72 watt. 0.72 watt per meter per Kelvin. So only 0.7 watts will be transferred per Kelvin. Okay. Now, this is the way that the conductivity is working for the gases, and for the air we have in terms of 0.026. For the bricks and for the water, like at rock, food, rubbers, we have in terms of tenses, and metals are having the wires, the 100, and lately we have yeah, this is the diamond and the silicon and the beryllium oxide and the quartz, the sand, for example, are having a very non-metallic crystals are having a very conductivity, high value of conductivity values. Okay, the thermal conductivity, and this is what called thermal conductivity. By the way, we have the conductivities, we have also electrical conductivity. It's also a conductivity, but that's in terms of volt, how much volts that we need to transfer, how much amperes of water of electricity will help to be. So conductive, it's a conductive material. It means that if you are talking about electricity, so it will the conductive and unconductive. The unconductive, it means the material that not let you to transfer the electricity. It means that it's an isolated thing. Okay. In this course, we are not talking about the electrical conductivity. Well, we're talking about thermal conductivities. Yeah, so we talked about the thermal conductivities, and here's also another. These are all the values that have been founded in the labs. Also, here's some kind of conductivity of the gases that we have with the temperature. We say that within the temperature, specific temperature, there will be a change in the conductivity. So for conductivity, for example, copper, if you want to change how much conductivity you need, if the copper was temperature was 100 Kelvin, and it will if it was 200 Kelvin. So in the 200 Kelvin, it means that you need 413 to increase 1 more Kelvin. While if we have the copper in 100 Kelvin, it means you need just 482 watt just to increase to another Kelvin. So we say that the temperature and the conductivity will be related to each other. It means that the increase of temperature will help you or will make the conductivity to be increased proportionally. This is for copper and this is for aluminum. So we have different conductivity for different materials. This is first, and for each of them there will be this value will be changed with the temperature as the base of the thermal conductivity. This is for room temperature. If you have a specific temperature, you want to increase 1 degree, you may have another point, another thing that we have value for the thermal conductivity K. As an example of the heat loss or heat transfer due to the convection, this is an example that we have the roof of an electrically heated home. We have this home. This is a home, and this home is electrically heated. It means that we have inside this home we have heater, and the area that we have due to this at about 6 meter by 8 meter, the area means the length multiplied by the width of this home is about 8 times 6 meter square. So within this area, it's made from concrete. It means that we have concrete roof. This concrete has a conductivity for the heat transfer. The conductivity for concrete is 0.8 watt per meter per degree Celsius. Now the temperature of the inner, so it means that inside the room we have hot weather, means 15 degrees Celsius, and outdoor the surface we have 4 degrees Celsius, that's in night. Now for 10 hours, it means that it will start from 8 to 8, that's 10 hours. Now determine the total heat loss, because we have inside the house, we have the temperature is 15 and outside is 4. So what will be happen? There will be a transfer from inside to outside. That's one thing. The other thing that we have to, so how much it will be transfer, how much is the heat transfer? We know that the solution will be look like this. The area of the roof is equal to width times the length, which is the 8 meter, it's equal to 8 meters times 6 meter, which is equal to 48 meters square. This is the surface area. This area is 48 meters. Now the heat transfer rate, it is equal to Q is equal to conductivity times the area times the delta T over the delta X, or the width, because the width of this is the width of this roof, 0.25 meter is the concrete width, roof width. So that will be also affect on the heat amount of the heat transfer. Now the conductivity of the concrete is 0.8 watt per meter Celsius times the 48 meters square, and times the delta T, which is we have outside, inside is 15 and outside is 4. So that means degrees Celsius divided by the width of this roof, which is 0.25 meter. Now this meter with this meter, I'll cancel out with the meter square. Degrees Celsius with degrees Celsius will cancel out. Now the Q naught, or how much is the amount of H, will be watt 0.08. It's 0.8 times 48 times 11 divided by 0.25, which means it means 0.8 times 48 times 11 divided by 0.25, so it's about 1.689 watt. 1.68, sorry, 0.8 times 48 times but it's 1.689 kilowatt. This is the answer of the how much it will be over that night. So over that night it will be 1.6. By the way, 1.68 kilowatt means 1.689 kilojoule per second, or kilowatt. Now this is for part 1. Part B, the cost of heat loss. So due to that heat loss, we have every there will be 1.689 hours will be kilowatt will be lost. So and I have 10 hours from that one. So due to that 10 hours over that night, so the Q is the total amount that we have of the kilowatt hours that have been lost due to that 10 hours. It means that the Q rate we have times the delta T, and that is 1.689 kilowatt times 10 hours. So it will be 16.89 kilowatt hour. Now how much is the cost of 1 kilowatt hour that will cost you? It will cost 0.08 kilowatt hour dollars. So it means the price of, for example, this heater, this house have been heated by electricity, so the cost of the electricity is 0.08. So the total cost is equal to 0.08 per dollars per kilowatt hour times the overall 16.89 kilowatt hours. So this will cancel out. So 16 times 8, 16.89, 16.89 times 0.08, it will be 1.35 to 1.3512 dollars. The cost of that 10 hours of the cost of the 10 hours of that night. Now this is the first thing that we have in the conductivity, and there is another method, and it's called convection heat transfer. So we say that we have three ways to heat transfer: conduction, and this is what the first thing. It means that we have delta T over delta X on times area times conductivity is the amount of the heat transfer due to the conductivity. Now we have another thing that is called convection. This is the convection. So how much is the heat transfer due to convection? I'm getting back to with another video. Thank you very much for listening, and I will be back with you for the convection heat transfer. Thank you, and see you in the next video.